Okay, this is the ENGR 312 Fluids Lab, lab number 6, the lab video. Okay, so we'll continue on the pump topic. Today we are going to use an experiment to verify the affinity law. Okay. Okay, let me share my screen to show you the handout I posted in Moodle. Okay. Okay, here it is. Okay. We already did 2 pump labs, right? Now we know how to measure the pump curve, system curve, okay? And we also know how to calculate and measure the pumping parallel, pumping series, okay? Today we're going to introduce another principle related to the pump. It's called affinity law. So first of all, I want to talk about what's the purpose of affinity law, okay? A couple of examples I want to give you before I introduce the equations. For example, you have old pump in the when the industrial application, let's say you have old pump, okay? So a common practice is we trim the impeller. You know, when the pump runs longer and the impeller gonna damage on the tip, okay? So it will perform, non-uniformly sometimes. So one practice is we trim the impeller. So the impeller becomes smaller. Okay, becomes smaller. It still work, but after you trim the impeller looks better and it will produce pretty uniform performance. However, that pump has a smaller impeller diameter and it will operate a little different comparing to the original pump. Okay, but it's still the same pump. It's similar, but it will perform differently. Okay, so the flow rate could be different, pump head could be different, and the power output could be different too. So before you actually install the trimmed impeller, trim the pump, you want to predict what's the future performance of the trimmed pump, right? So that's what we use in affinity law. Try to predict the future performance in terms of Q flow rate, in terms of the pump head, and in terms of the power. Okay. Another example could be like you have the same pump. The newer pump, you have like a variable speed pump, right? You can change the RPM a little bit, and it will run differently. But you want to also predict maybe when you run a different RPM, what the pump will perform. What is the flow rate? What is the pump head? And what is the power? Okay, when you run a different RPMs. So that's the purpose of the affinity law. Affinity law try to predict the performance when you change one or multiple pump parameters, such as diameter, such as RPMs, such as even you can include the density of the fluid. When the same pump run for different fluid, okay, with different density of the fluid, what will be the performance? Okay, so that's the purpose of the affinity law. Okay, this is the handout, equation 1, 2, and 3. These are the 3 affinity law equations. Okay, so let's look at all 3 of them. Okay. See, the first equation is flow rate equation, Q2 and Q1. Let's assume Q1 is the original. Subscription 1 is the original pump. Okay, so if you move Q1 to the left-hand side, it's a ratio, Q2 over Q1. So Q2 is flow rate for the newer pump, so the new pump, right, with the change. So the ratio basically equals, so if you know the original flow rate, then if you know the ratio, you can predict the new flow rate, right? So the ratio equals N2 over N1. N is RPM. Okay, D2 over D1 is D is the diameter of the pump. Okay, so basically this equation works for both applications I just mentioned earlier. Okay, if you trim the impeller, so the diameter changes. Okay, diameter changes, but you will run at the same RPM, the same pump, right? Same RPM. Okay, so with the diameter change, you can predict the Q2 based on the original flow rate Q1. Okay, Q2 over Q1 equals to N2 over N1 times D2 over D1. That's for the flow rate. Let's say for the pump head, HP2 over HP1 will be equals to, okay, it's a RPM ratio square, okay, times diameter ratio square times the density ratio. Okay, so again, when we trim the impeller, D2 over D1, you have a have a value, right? Not 1, right? N2 and over N1 will be the same if you keep the same RPM. If you run in the same fluid, rho 2 over rho 1 is still 1. Okay, so basically the pump head ratio between the new one and the old one will be diameter ratio square. Okay, but if your application is, we're not trimming the diameter, we just run the pump with different RPM. Then the pump head ratio is actually the RPM ratio square. Your diameter will be the same, right? Density will be the same. So it will be RPM ratio square. Okay, you can predict the new pump head. Okay, the pump head for the new pump. Or if you have exactly same pump, you're running on different fluid. Rho 2 over rho 1 is the ratio for the density. So based on the fluid property, you can predict actually my new pump HP2 over HP1 will be equals to the density ratio. Okay, see here we can have 3 applications there, right? When you change the pump a little bit. But for the flow rate equation, there's no density ratio there. Okay. Then for the power output, W2 over W1 equals to the RPM ratio cube times diameter ratio cube times density ratio. Okay, so depending on your application. If you trim the impeller, the other 2 ratios are the same. So it's still 1, then your diameter ratio cube is your actually the power output ratio. Brake horsepower, right? Okay, so these are the affinity law 3 equations. So you can predict the new flow rate, new pump head, and the new W power, okay, based on the change, either the RPM or change the diameter or change the running operating fluid. Okay, so you can predict the new performance. Okay, the assumption here is the change is small. Okay, its change is not that much. We assume that the efficiency of the pump keep about the same. Then the affinity law will be satisfied, will stand. Okay, if you really change a lot, then it won't be accurate, the affinity law. Okay. So here, equation 4 listed the power equation. I hope you still remember in fluids, right? Pump head times flow rate times gamma. Gamma is a specific weight of the fluid. Okay, rho g basically. Okay. So in the lab, in this lab number 6, okay, we use the same pump as the lab number 5, right? There's no way we can trim the impeller, okay? Diameter, we won't be able to change the diameter for the pump, okay? So the diameter ratio here is the same. One, we run the same fluid water, the density ratio is the same too, okay? Density ratio is also 1, it doesn't change. Okay? Only thing we can change is RPM, right? That's a variable speed pump, so we can easily change the RPM of the pump. So we have a RPM ratio, so you can predict your flow rate. Okay, based on, let's assume the first RPM is the original one, okay? So you know the flow rate. Then when you change the RPM, you should be able to predict the new flow rate, the new pump head, and the new power. Okay. So in this lab, I want you to compare the ratio. Okay, basically this three equation, Q2 over Q1, HP2 over HP1, and W2 over W1 equals the right-hand side. This is a theoretical prediction. Okay, this is theoretical prediction. Okay, without running the experiment, you should be able to know. Okay, so if you set 2 RPM levels, for example, one is 90%, one is 60%, one is 2000 RPM, one is 1500 RPM, for example. So you should predict your flow rate ratio, Q2 over Q1 equals to 2000 over 1500. I make up the numbers, and actually the measurement number is different. Okay, but you should be able to predict. This is prediction. Okay. Also, HP2 over HP1 will be your RPM ratio square. Okay, so W2 over W1 will be RPM ratio Q. Okay, that's a prediction. You can also record in the experiment when you set the 2 RPMs. You can record the flow rate 2 and the flow rate 1, right? You can record the HP2 and HP1, W2 over W1. So you can record them, and that's your measured flow rate ratio and the measured pump head ratio and the measured power ratio. So your measured ratio, I want you to compare to the theoretical ratio by equation 1, 2, and 3. Okay, is that clear? So that's the lab number 6 affinity law. The requirement is here. I want you to produce 2 pump curves, okay, for the 2 pumps you want to try. Basically, 1 pump with different RPMs, right? We assume it's 2 pumps, okay? So I think you already did the pump curve lab before. You know how to changing the speed, right? You're using change the valves, okay, to have multiple readings on flow rate and the pump head. Okay, that's how you produce a pump curve. Now you need to produce 2 pump curves here. Okay, one for the 1 RPM, the other for the other RPM. Okay, then plot the 2 pump curves. Then you need to compare the ratios. Okay, I will talk about the more detail later part of the video. But here I want to say, hey, so for every pair of points, that ratio has to satisfy the affinity law, right? What does that mean? What do you mean by pair of points? Basically, on each system, on every setting, every system, the affinity law satisfies. So in that sense, every time you open a valve to a opening, that's considered a system, right? So you have to measure both pump in that valve opening in that same condition. Okay, so when you set the same RPM, you set the same valve opening, you switch the RPM back and forth, get the 2 pump measured for the flow rate, pump head, and the W. Okay, then the Q between these two RPMs, the HP between the 2 RPMs and W's between the 2 RPMs should satisfy the affinity law. Okay, so that's what I want you to verify the 3 ratios. Okay, predict the ratio by equation 1, 2, 3, as well as compared to the measured ratio, directly measure the ratio for flow rates, HP and W's. Okay, then discuss the finding as well as related to physics. Okay, that's a lab requirement. Okay. Next, let's look at the pump, and then I'll talk to you about a little bit more detail about the measurement.